So there's something that we now notice from this expression, that V is no longer dependent on just a minute. Here, I will just remove that, because as you can see, when we did the integration, the R changed from being R squared to being R, and therefore this equation actually expresses the V at point R or at point B, which has position vector R. So again, this is a very clear observation that we have made from our derivation that we have just done right at this point, that the dependence of V with the point of observation R stops being a square or in a square, but rather becomes just without square. So from equation 462, we note that from equation 462 that the equation that electric field strength E points in the radial direction. That is something I've already said. Any contribution from the displacement theta and phi is wiped out by a dot product. This is something that you observe, that we are saying that E, if you are considering to be 462, this is equation 462 right here. I think I have filled my screen. I can come a time where I cleanse it. This thing is hanging. Just a minute. I stopped recording. I don't know what happened, but I have resumed. So I was just saying that from the observation that we have seen is that a vector E has the effect by the displacement towards theta or phi is cancelled out and the only effect that is left is the radio effect, or the radio vector that moves towards away from the source of the field E, and therefore the theta and the phi component is lost or cancels out. And we have said that such a vector is called conservative vector, which is also called rotational. And since we defined rotational as the one that has no component that is rotating, then we are saying that the curl of E will actually be zero. It's actually zero. So we have concluded that E is conservative. Now we need to define something else, that that is the potential at any point is the potential difference between that point and a chosen point at which the potential is zero. So that is the general definition of potential. And as I have expressed in the previous example, I have said that if you consider your source to be Q, and you have sought the point of observation to be P, and the reference point is of Q is infinity, that means you are moving this charge from infinity towards point P, and this one is outward. You know that I'm assuming this is positive, and this is positive. So we said that when you reach this Q at point P, then it will have achieved some potential V that can be expressed as the point, the V at point P. If you call this one A and you call this, let me call this point B. So you want to find potential at point B, you're simply saying that it's going to be AB, which means that there's potential at B due to A. And that is what this statement means. Okay, so in other words, if one assumes zero potential at infinity, we always consider that the potential at infinity is zero. It keeps it increasing as you move from infinity towards your point of observation, point B. Then that is one assumption that we always make. Then the potential at a distance r from the point charge is the work done per unit charge by an external agent. The one I was saying that I was moving this charge from here towards point B, that the potential at distance r, and you're saying that r now is this one. The potential at distance r from the point charge q is the work done per unit charge by an external agent. So I'm the one who did this work to bring the q positive from here to point B, and therefore I'm an external agent. In transferring a test charge, my test charge is q, the small q, from infinity, my infinity was here, to that point by point B. And therefore, we have said that V is expressed as negative infinity, a negative integral from infinity to point R, of course, of the integral of E dot dl. And so this is the one that we can simplify further and express now as the source and the field points. And I think this is what I was, the diagram here is the one I was trying to express at this point. And probably this is actually much clearer. This is my point at origin. Probably I can bring this diagram here. Sorry. Let me draw another one. Assume that is the origin. So assume, hope I can change the color of this. How do I do that? Let me see. Oh, I don't know how to do that. Let me delete it again. Can I get change the color? Just a minute. I think I don't want to waste your time. Let me just change the color, then get this shape, draw it afresh, then bring it here. So I've just drawn that as a quick diagram, and I'm saying that assume that this figure, I'm trying to evaluate the field or the potential at point origin, which is the one I am labeling now as point O. Of course, it is 0.000. And therefore, we have a point charge, which is point Q. And we are bringing this point charge from infinity, which is our test charge, to point B, which is our point of observation. And then therefore, we are saying that the source point, the source position vector is R1, R prime. This is a bit hidden. Let me see if I can move it slightly, or rather, there. How we? Scalar. Oh. Yeah, I think I want to move it there. So that, yeah. So I wanted to move it so that you can see. I'm just assume that the same thing, that this point is still at the, assume that this point is at the origin, and therefore the position vector, which I'm now expressing, R1 is the position vector of the source, of point of the source, and R is the position vector of my observation point, which is Q. Therefore, the idea is that the potential so I was actually reading this statement saying that if the point Q is not located at the origin, but at a point whose position vector is R prime, that way I have shown you here, then the potential V XYZ, or simply VR, at this point, only observing it at point P, or which is the one I'm pointing at now, then we can always say that it is going to be given by Q over 4 pi R minus R prime. And of course, that it's on point R prime. Here is a point I needed to make sure that we confirm. I think here I made a slight mistake. So we are saying that they are, I can express this one as this being my source, this being my field point or point of observation. Observation point. And therefore, you can always say that it is equivalent to R minus R prime. That is always what we do. We normally interchange. Whenever you see this kind of thing, when you want now to do the magnitude, you say you normally interchange them. You find R minus R prime. So that is what I was trying to do there, and it takes this shape. So we have considered the electric potential due to a point charge. Now, what we have done is just we were trying to express the electric potential due to a point charge. Now, the same basic ideas applies to other types of charge distribution. Remember, we were dealing with many other type of charge distribution. If I just remind you, we were dealing with the point charge is our first one, and that is what we have already dealt with. Then we also said that we can deal with an infinite line, which is charged, so line charge. Then we also said about infinite service, which is charge distribution, and you can also say finite sphere, which is having some volume. So we can always consider all those things. So that is what the point I'm saying, that the simplest example that we have considered is for the point charge, but then you can also consider other kind of charge distribution. I have just expressed at that point. So the same basic ideas applies, but before we even go to the infinite line or infinite service, we consider that, assume you have more than one, you have more than one charge. You have Q1 there, you have another Q2 there, and you have another Q3 there, and you want to bring some charge from infinity to this point. So this is my point infinity. You are bringing it towards point B, which is going to have to experience some resistance. Just try to figure out that this one is a positive charge, this is a positive charge, and this is a positive charge. If you are bringing some small charge Q, which is also positive, that means when you bring it towards this point, it's going to have some repulsion due to charge Q1. It is going to be repelled by Q2 is going to be repelled by Q3. So the same thing, and the repulsion is the one that builds. So the repulsion is the one that builds the potential. Like I'm calling it the one that builds the potential. The more this charge is repelled, the more the charge Q1, the test charge is repelled, therefore the higher the potential that it gains, or the more work I do from as I bring it from the negative infinity, from infinity towards this point B. So having said that, therefore we are saying that the total potential that the Q attains as it moves from infinity towards point B is simply going to be the total potentials that it would gain if these charges or these point charges were there individually. So you'll see that it is going to be the sum total. We are applying the superposition principle that says that the total will be equal to the sum. Therefore, you get the potential due to Q1, the potential due to Q2, all of them until the potential due to Qn, you add them and you get the potential at point R due to all these charges. And that is what equation 466 says, just expressed in the summation format. And now we're saying that, so you have considered assuming you had many charges. Now, consider now we have continuous charge distributions. That is, you have a line charge like the one I mentioned, you have an infinite line, infinite service, or a finite sphere. What will happen? How much potential will each of those cause? So again, they are expressed, as you can see here, without much trouble. You can be able to say that the only thing we are changing from this point is the Q, which we are saying that you can replace the Q that we had probably at this point, if you had only one, and you replace it with, if it was a line charge, it will simply say that Q is equal to raw R, that is line charge density, and then with elemental length dl, of course, you then integrate, and that will give you this is over the length of the line. That will give you the total charge that my line has. And if it is infinite, then it will simply give you this expression in 467. Now, of course, if it is service charge, remember we said that Q for service charge will be expressed as rho S ds, but then there is an element of service. Therefore, if you consider the total service, it will simply become the service integral expressed as equation 468. And last but not least, if it is volume, you say that Q is going to be given by rho V dV, and therefore for the entire volume, just integrate over the entire volume V. Therefore, that nothing changes much except that being told that it is 12 p.m. We have spent 1 hour. We have 1 more hour to go. I probably need to move slightly faster so that you can finish what you have planned to do. So the idea here we need to confirm here is that the primed coordinates, because customarily used to note the source, just like we said here, the source is primed, and the one that is not primed is the observation point. And that is what I actually was pointing at that point. So, and of course, the unprimed coordinates are referred to the field point, or the point at which V is determined or being observed, etc. So the following points should be noted. We recall that, of course, I just need to summarize. I can see someone needs a break. I'm going to pause in 2 minutes or shortly. So we want to observe the following points. That we recall that equation 463 to 69, 463 to 69. Yeah, all these equations that we have been talking about potential, the zero potential reference has been chosen arbitrarily to be at infinity. If any other point is chosen, then equation 4.3 becomes equation 463. So we are saying that we have been choosing, let's 463. This is, we assume that where am I? I need to wrap this. So yeah. So this is my equation 463, and we're saying that we have assumed that the reference point is infinity. So if it is not infinity and we wanted to integrate, we are actually going to see that that equation will have a constant c, where constant is chosen to be the potential at the reference point. So we have been saying that the potential at infinity, we have been saying that the potential at infinity is that infinity is equal to 0. Therefore, if it is not infinity, then it is not going to be equal to 0. So if it is a point of observation is less than infinity, then it is not going to be equal to 0. And therefore, it is going to be equal to a constant. That is what that this equation 470 is saying. So the same idea applies even for the others. So here, if you are not referring with the source moving your reference point being at infinity, you would consider adding a constant here, adding a constant there, adding a constant there, and that means that your reference point will not be 0. The last point that we observe before we go for break is the following: that that the potential at a point can be determined in 2 ways depending on whether the charge distribution is known. Okay, the charge distribution is known, or electric field strength E is known. If the charge distribution is known, we use one of the equations 465 to 470. We can always use either of those ones. If you know the charge, then we use this equation 470 from 465 to 470, because all of them are using the amount of charge. You can see every one of these is using the charge. This one is using the charge Q plus Q1, Q2, Q3, or even Q. All of the starting point is knowing the charge. If you don't know the charge, the point we are actually saying is that we can now use E, and we are saying that we can depend if we don't know the charge distribution, then we use one of the equations 465. Sorry, if we only know E, that we do not know the charge, that means we actually use the equation 471. Okay, so the idea was this one. So if we know Q, then we use equation 470, 465 to 470. If we know E, then we use equation 471. And the potential VAB can simply be found from this equation 471. We can simply say that it's going to be given by V, just the integral of this from point A, point B, that is the source, to the point of observation. And it will simply be the work per unit charge as expressed by equation 472.